Hello everyone. Here we're going to look at how we use the graphical method to locate the optimal solution for a minimization question. So again, there's been a lot of work that we've done leading up to this point, starting with creating the mathematical model or linear program itself. From there, we went and graphed the constraints, and after having graphed the constraints, we used those constraints to identify the feasible region, and we got to a point that looks something like this. So on this, we have now identified our feasible region, which is this region shaded in green. Again, if any of that doesn't make sense, creating the mathematical model, being able to graph the constraints, being able to use those constraints to identify the feasible region, please review the prior videos. From here, we are going forward and now using all that previous work in order to locate the optimal solution on this graph. So the one thing we learned in a previous video about the optimal solution is that we know the optimal solution is going to happen at one of our critical junction points or our apex points, however you want to refer to them. So even though anything in this shaded region, and this region goes on and on forever, like it's not bound here, it's just stopped shading because that's as high as the graph went, but it keeps going on and on forever this way and on forever this way. But I know that the optimal solution here should occur at one of these apex points, either where constraint 1 meets the y-axis, where constraint 1 meets constraint 2 meets constraint 3, or constraint 3 meets the x-axis. Even though this area is infinitely large, anything in that region is a possible solution. It means there's a possible infinite amount of solutions for this question. For this minimization problem, the only points that could be an optimal solution are 1, 2, 3, 4 intersection points. I know that one of those points is going to be my optimal solution. It's now on me to graph the objective function, going back to our model, the objective function, graphing this is what will allow me to find which of those 4 intersection points will be the optimal solution point. And as we learned in our last video, that in its current state, 0.97a plus 1.89b, I cannot graph this on here. This is not the equation of a line. This is not something I can graph on any graph. I need that to be equal to some value. Right? I can only graph the equation of a line, and without an equal sign, this is not an equation. So I'm going to choose some arbitrary number to set that formula equal to something. And you can choose any value. Here I happen to choose 5. Now, we saw in a previous video that I tried to choose a value that sort of worked out with the numbers that I had. Right? I chose a value of 15,000 because it was a multiple of both 5,000 and 3,000. Here, where we're dealing with decimals, it's probably not going to be able to find a number that's going to work out nice and pretty like the last one did. So you still want to choose a number that's going to help it graph onto the current scale that you have. We're going to now graph this exactly as we had graphed the constraints in the past. Initially setting a to be equal to 0, well, subbing in 0 for a, we now get 1.89b is equal to 5. b is equal to 5 divided by 1.89, or b is equal to 2.64 and a whole bunch of other decimals. So I'm just going to do the best I can to graph that somewhere on this. It's somewhere in between 2 and 3 and a little closer to 3. With that, I'm now going to go and find my second point. So now subbing in 0 for b, I get 0.97a is equal to 5. A is equal to 5 divided by 0.97, or a is equal to 5.15, and again, a lot of decimals. So I'm going to try my best to get that on. It is a point slightly above 5. And with those 2 points, I can now connect a straight line between them, and I have the starting point for my objective function. Prior to locating the optimal solution, there was no difference as to whether I was dealing with a maximization or a minimization problem. I graph the constraints in exactly the same way. I find the feasible region in exactly the same way. Now, identifying the optimal solution is absolutely different between a maximization or a minimization problem. With a maximization problem, I want the area in the feasible region that is absolutely as far from 0, 0 as possible. Now that I'm dealing with a minimization problem, I want the point in this feasible region that is absolutely as close to 0, 0 as possible. So remember, that line was just graphed to get a starting point. Now I'm going to slide that, keeping the slope of that red line the exact same. I'm going to slide that until I find the point as absolutely close to 0, 0 as possible. So as I'm sliding this way, it's when I first just touch this region. And now that I've done that, I can see that that is the closest point based on the slope of this line to 0, 0, meaning that my optimal solution is at this intersection point where constraint 2 and constraint 3 meet. So remember, that will not always be the optimal solution in terms of this question. That is only the optimal solution based on the slope of this line. Had the values of the cost of fertilizer A and fertilizer B been different, that's what would have adjusted my slope. With different values for the cost of A or the cost for B, that would give me a either more dramatic slope or a less dramatic. So either a steeper slope or sort of a less steep slope. If I look back at what the line looked like, if that line was much more steep, so more straight up and down, well, then I would have either hit, depending on how straight up and down it was, my point closest to the origin would have either been here if it was very much straight up and down, or if it was a little more angled, like something like this, then I would have hit this point as my optimal solution. If that point was much flatter, nearly horizontal, then I would have hit this intersection point, constraint 3 and the x-axis, as my optimal solution. We don't guess what that optimal solution point is. We graph the objective function and then use the slope of that objective function to help us identify which of those points would be where the optimal solution is. And as we said in this case, based on the cost of fertilizer A being 97 cents and the cost of fertilizer B being $1.89, that gave me the slope that I'm currently dealing with and allowed me to find that the optimal solution in this case is where constraint 2 and constraint 3 meet. So stay tuned for our next video in which we will find how we mathematically find what the values for A and B are at this point. As always, please email me with any questions that you have.